Hello and welcome from the U.S. Space and Rocket Center. I'm your host, Joseph Vick, the Museum Education Director, and we're going to be talking about asteroids, building an asteroid, and learning about where they're from. But first, what is an asteroid? Asteroids are fragments left over from the building of the solar system over 4.5 billion years ago. Some are car, building, or even small city-sized space rocks. The largest asteroid, named Ceres in the asteroid belt, is even considered a dwarf planet. All asteroids exhibit craters, big and small. They tell us about the formation and history of the solar system. Some have loose particles on their surfaces, while others are bare rock. Where are asteroids found? The majority of asteroids in our solar system can be found in the asteroid belt, located between the planets Jupiter and Mars. The asteroid belt is 93 million miles wide. That's the same distance Earth is from the Sun. There are millions of asteroids found inside the asteroid belt, but even if you combine the entire mass of the asteroid belt, NASA scientists predict the object would still be smaller than Earth's moon. Not all asteroids in our solar system are found within the asteroid belt. Some escaped, some were ejected through collision and bounced outside the asteroid belt. Some became moons, like Phobos and Deimos of planet Mars. Some are close to Earth, and we call them near-Earth asteroids, like asteroid Bennu. And even though it's considered near Earth, it's still 200 million miles away. There are three main types of asteroids. The first is C-type, for carbonaceous chondrites. They are considered the most common and are made of clay and silicate rock material. They're mostly dark in appearance and are considered by asteroid scientists to be the most ancient objects in our solar system. The second type is S-type. S stands for stony, which are made of silicate materials, and some contained nickel-iron metals. The third type is M-type. M for metallic. Metallic in the form of metal, nickel, iron, exposed or within the core, and they are characterized with solidified lava rocky surfaces. Asteroids commonly collide into one another. As this happens, material is piled up and transferred from one asteroid to another, making one larger. This process is called accretion. Gravity helps with this process. The force of gravity pulling the material inward towards the center of the asteroid. If enough gravitational accretion happens over long periods of time, as in millions or billions of years, a planet can be formed from the buildup of mass. This buildup of mass can lead to melted materials, and over time more accreted material will push other materials into the core or center of the asteroid. These heavy materials are mostly metals. These metal core asteroids are known as differentiated asteroids. Vesta is a differentiated asteroid and is also the brightest asteroid visible from Earth in the asteroid belt. Planet Earth is considered a differentiated planet because it too has a metal core and upper crust. So let's make an asteroid. You'll need the following materials. Clay in different colors. Black and gray are good realistic colors, but you can have any color asteroid you would like. Sand in different colors. Rocks that you find out in your backyard, or you can have aquarium gravel. Marble or metal ball bearings of different sizes or shapes, or even small bouncy balls made of rubber or ping pong balls made of plastic. Measuring spoons and or other objects with rounded profiles to make craters. You can also use your fingers to make craters as well. Each person selects clay as desired color and adds silicates, rocks or sand, to their asteroid. In doing so, you will make an awesome one-of-a-kind asteroid. For a rubble pile asteroid, gently combine different clay and rocks to form a loose conglomeration of materials. leave some space between the fragments. For an asteroid that has melted, start with a metal ball bearing and layer different colored clays over it. The outer portion might look rocky, but the metal in the inside is the core. Add some craters, big and small, using the spoon or your fingers. Overlap a few of them where asteroids collided in the same area at different times. Discussion questions. Is your asteroid strong enough to withstand a collision with another asteroid? Try it out, either with a friend or build two asteroids to collide together. How would your asteroid reflect sunlight as it spins? Take a flashlight, shine it on your asteroid, and turn your asteroid. Are there any more reflective areas on or around your asteroid? What's causing those reflective areas? Let's now review some really cool current and future NASA asteroid missions. I also wanted to acknowledge the sponsor of this video, the Marshall Space Flight Center's Planetary Missions Program. And if you want to learn more about these deep space missions and many others like them, please check out their website at nasa.gov/planetary missions. The Origins Spectral Interpretation, Resource Identification and Security Regolith Explorer OSIRIS-REx mission was launched in 2016. OSIRIS-REx reached and began exploring the near-Earth asteroid Bennu in 2018. On October 20, 2020, OSIRIS-REx collected an asteroid sample in a technical touch-and-go tag procedure. That tag return sample is planned to reach Earth in 2023. The Double Asteroid Redirection Test DART mission is a planetary defense-driven test of technologies for preventing an impact of Earth by a hazardous asteroid. DART will be the first demonstration of the kinetic impactor technique to change the motion of an asteroid in space. The DART spacecraft will achieve the kinetic impact deflection by deliberately crashing itself into the asteroid. The DART mission has a future launch window of November 2021 through February 2022. Lucy will launch in October 2021, and with boost from Earth's gravity, will complete a 12-year journey to 8 different asteroids. Lucy will be the first space mission to study the Trojans. Trojan asteroids are asteroids that share a specialized orbit with a planet, especially Jupiter. Lucy's complex path will take it to clusters of Trojan asteroids and give NASA the first close-up view of all 3 major types of space rocks. The Psyche mission, set for launch in 2022, is a journey to asteroid Psyche, a unique metal asteroid orbiting within our solar system's asteroid belt. What makes the asteroid Psyche unique is that it appears to be the exposed nickel-iron core of an early planet, one of the building blocks of our solar system. Deep within rocky terrestrial planets, including Earth, we cannot see or measure Earth's core directly. Psyche offers a unique window into the history of collisions and accretion that created terrestrial planets. The Psyche mission will also test a sophisticated new laser communication technology that encodes data in photons rather than radio waves to communicate between a probe in deep space and Earth. Using light instead of radio allows the spacecraft to communicate more data in a given amount of time, with NASA scientists back on Earth. For the next part of our activity, we're going to need to go outdoors, where we're going to see how our asteroid samples can create what we call craters. So if you don't want to use your asteroid sample, you can also use ping pong balls or marbles that we had before so that you can see the impact of your crater. But before we go outside, I need to change first for our experiment outdoors. Hello and welcome from the surface of the moon. I am currently inside of a moon crater. So I wanted to go over with you some basic parts of a crater. I'm currently standing on what is considered the floor of the crater. Just like the classroom or room you're in at home, there is the floor that you are standing on. So I am currently in the floor of the crater. In the center of the floor, you have, in a complex crater, a central uplift, what looks like a small little mountain in the center of the crater. I am currently standing on that central uplift. That central uplift is here because of that impact of that asteroid that hits that crater in the center. Just like the floor of a crater and the floor of your room, you also have walls. So here is the wall of the crater that I'm currently standing on. It goes all the way around and has a slight incline, an incline that goes all the way to the top, to the rim. To the rim. Think of it like a bowl, like the bowl of cereal that you ate for breakfast this morning, that has the very rim at the edge of your crater bowl or cereal bowl. We built an asteroid for part 1, but part 2, we're gonna make our own craters. Okay, let's start with our activity. So I have here some setup tools that we can use to form our craters. I have made one already here as an example, but I'm going to make one for you so you can know how to make your own at home or in the classroom. I still have the supplies left over from when we made, in part 1, our asteroids. So I'm going to use the soils to make layers. All planets and moons, including Earth and our moon, and even Mars, have layers as the planets were formed and built over time. So we're going to have layers so that when we see that impact occur from our asteroid, we get to see those layers in that crater formation. So first, I'm going to have the sand from earlier and sprinkle it on the top of what is a flour layer. So I added flour on the top. If you don't have flour, sand of a different color works just fine as well. Next, I have a darker sand or soil mixture here of a reddish color. So it's in contrast to that lighter sand and flour mixture. A very light dusting on the top is all you need. And then last, I have a dark sand material, very similar to what is in the middle of our moon crater. So moon surface. Again, a light sprinkled layer over the top. If you see some of the layers below, that is just fine as well. Our next step is to gather your asteroid that you made earlier. Again, observe your asteroid, look at your great work that you did in building your asteroid, because this asteroid is going to be and make the impact crater on the surface of your planet that you just put together. So I'm going to measure the distance using a meter stick. If you don't have a meter stick, you can do it from your arm extended drop into the bowl, but I'm going to use it as a measurement reference. And it's also good to have a smaller ruler to measure the width of our crater and depth of our crater once we form our crater in our bowl. So let's get started. I have my measurement there at the surface of my planet or moon. I have the asteroid at the very top of my meter stick. And with a countdown from 3, 2, 1, I have impact. So I'm going to do another crater for us today, and I encourage you to do multiple craters and multiple measurements. And in 3, 2, 1, another drop. This one seems to be a larger impact crater. It seems to be much deeper. So I'm going to remove our asteroid here and set it to the side. Ooh, look at that one. You got a nice central uplift there in the center with that darker material from the top as it was pushed down. And it is much deeper than before. It looks like we have about almost 3 centimeters off to the side of our wall. And what width do we have here? Almost 7.5, 8 centimeters across. But there are other parts with our impact that make the crater what I consider beautiful. You have all of this material that was ejected are moved out of the way, we call that ejecta. All of these layers where that asteroid impacted have to go somewhere outside of that crater bowl that was formed. So they're ejected out and form what's considered a pattern in the form of rays. Just like if you draw a picture of the sun, you have all of the rays of light coming out and around from the center of the sun, just like rays of a crater that extend outward from that impact of your asteroid. Now that I've cleaned up my experiment, I'm going to walk up the ladder and enter my capsule for my return back to the Earth. You are scientists. You did an experiment today, and you are the future scientists, engineers, and astronauts. And one day, you may be that astronaut, scientist, or engineer that walks on the surface of the moon. Until that day, I'm going to load in my capsule and return to Earth.